Molecular shape and geometry is motivated by trying to keep everything apart in space. So if you have lone pairs or if you have a bonded atom, you'd like to arrange them as far apart as possible. It's called valence shell electron pair repulsion. That is, you have electron pairs in either bonds or lone pairs, and they repel each other, and you'd like to distribute them in space as far apart as possible. So how do you do that? Well, you know the steric number is the number of lone pairs and the number of bonded atoms. That tells you how many things you have to distribute in space. We can look at that for several examples. For instance, if we have 6 things distributed in space, here are 6 balloons distributed around a central point. And the balloons touching each other demonstrates the steric interaction, how everything is trying to spread itself out as far as possible in space. And what you get is this kind of arrangement. In this arrangement, all the positions are equivalent. Even though I've got red and yellow balloons, the yellow balloons or the green balloons could be on top. Each position is identical. But what you have here is an octahedral shape. An octahedral shape is 6 things arranged around a central point, 6 vertices. Now, it's called an octahedron because these 6 vertices form a shape with 8 sides. So 6 things is an 8-sided figure. The octahedron is an arrangement of 6 things around a central point. Each bond angle is 90 degrees. So all the positions are equivalent. So 6 things, octahedral shape, all the positions are equivalent. What if I had 5 things? Well, with a balloon, it's easy to go from 6 to 5. I'll take away one position, this one, and go to 5 things. 5 things in space. Now I'm glad I have yellow and green balloons, because when 5 things arrange themselves in space, and you saw I gave it a little jiggly vibrational energy to help them arrange themselves in space, now I have 2 different positions. I have positions that we call axial and positions that we call equatorial. 5 things in space, 2 bond angles to describe. So I have a bond angle of 90 here and a bond angle of 120 about the equatorial positions. So here's a 90-degree bond angle between green and yellow, but the green-greens are 120 degrees. 5 things. We call this a trigonal bipyramid. So it's 2 triangular pyramids on top of each other. Trigonal bipyramidal is the name if we give that shape. Let's go down to 4 things. We'll lose one more of our balloons. 4 things. Now here's a tetrahedral shape. Notice that these 4 things don't naturally arrange themselves as a square plane. I could probably force them into a square planar configuration, but I have to hold them there. If you give this any freedom, it naturally arranges itself in a tetrahedral shape, where these 2 point out at you, these 2 back beside you, and that's often the way we represent this. Here's tetrahedral. Each angle, 109.5. And think about that. 109.5, that's a bigger angle than 90 degrees if it were square planar. So if I squish this into square planar, things are closer together. These are 90-degree angles, where the better arrangement, tetrahedral, they're 109 degrees from each other. So you can see this VSEPR arrangement is better energetically. The electron pairs have bigger angles, more space between them. And of course I could continue, could pop another balloon. I don't think we have to pop a balloon to go down to the trigonal arrangement. That's 3 things arranged in space. We know those are in a plane. Whenever you have 3 points, you define a plane. So 3 things, steric number 3 gives you a trigonal arrangement. Bond angles 120 degrees. And I think you know 2 things arranged in space linearly, 180 degrees would be the bond angle. So steric number determines a VSEPR shape, and that's going to determine the overall distribution of lone pairs and bonded pairs and determine molecular geometry.